We are trying to integrate vector-valued functions now on surfaces. In order to understand this section, by the way, you must understand how we integrate scalar-valued function on the surfaces to begin with. Let's again go back to the two-dimensional case. We have a curve in the plane. We know that integrating a vector field along this curve also depends on the direction that the curve is parameterized. And in order to have Green's theorem hold, we need this orientation to be the right way, positively oriented called. In the case of a simple closed curve in the plane, if one orientation doesn't work, then the opposite does work. So if you started with some orientation and you calculated and you saw that the Green's function doesn't hold, you would exactly be off by one negative sign. So instead of proving a equal b, you would have a is equal to negative b. That would say, wait a second, your orientation was wrong the whole time. So you go back and you reverse your orientation and everything is fine. So given a simple closed curve in the plane, either one of the orientations will work out. And a notion that makes sense for such domains is that of outward normal vector. And the keyword here is D. So if you are on your curve, there is an unequivocal, unique, identifiable vector that is first of all perpendicular to the curve, has unit length, and points outside the region. This vector is always there. It can be defined. And why I'm making a big deal out of this will be apparent when we discuss surfaces. And I also want to point out and remind this one particular case of Green's theorem. If you integrate a vector field f by dotting it with this normal outward vector, and your f is given by pi plus qj, then it ends up being equal to this quantity's integral over the interior, which is the divergence theorem in two dimensions, and a simple consequence of Green's theorem, which we did calculate to show. Now we want to do similar things in 3D. We will have a surface enclosing a volume, just like how we have had a curve enclosing a domain. So now in this surface, we want to integrate a vector field. So the vector field is defined on maybe all of R3, at least on some open set containing this whole business. And now I want to make sense of what is integral of f on the surface. So what should this mean? And remember that we know what integral of a scalar function means on the surface. So this is in hand, and we want to define this other one. If we compare to the last integral above that I showed, one way of doing this will be to dot product f with some vector and then integrate the resulting scalar valued function. But what should be this mysterious vector that we dot f into? Of course, this has to do with the surface S, and one candidate would be, okay, let's go into this surface at every point. We look at the tangent plane, and then there is the normal to that tangent plane. We can also take it to have length 1. So it's a unit length normal vector to the surface, and it points. Now we can have two directions, so we have to mention if it points into or out of the enclosed volume. So simple, right? So at every point we take it to be that vector, and we dot product, we have a scalar function, and we integrate. Perfect, right? Unfortunately, this is not the case. There is no such "the" in the world of surfaces, unlike in 2D where it always existed. You look at a curve enclosing a domain, either your vector points in or out, and you consistently can choose this vector all throughout. Unfortunately, for surfaces, it is not a given fact that we will have the unit length vector to the surface consistently defined. And the prime example of this is what is called a Mobius band. It's a surface sitting in the 3D to which you cannot consistently assign this unit normal vectors. So let's say you pick this here, and then of course you go here, and you think you will consistently just assign this normal everywhere, and this surface goes along and then returns to itself. And once you consistently follow this path and assign vectors, all of a sudden when you reach back here, you see that the vector has ended up on the opposite side. It's now pointing downward. So this assignment of the normal vector is not consistent. It's not continuous. So this point and this point are very close, but all of a sudden the vector assigned here is pointing in the complete opposite direction to that. So for some surfaces, this assignment of the unit normal vector cannot be done easily. And that's why we will look at surfaces that are so-called orientable, the ones where this assignment can be carried out. The surface, for example, is orientable because you can just put this outward normal everywhere, and you can imagine that there will be no problem in consistently doing this. Even in the back that I'm unable to draw, there will be no contradiction, so everything will fit together, so this picture will work. The case of a torus similarly can work. A torus, you can assign a normal vector at every point. I think you can just take something like that, and it rotates along these circles of that torus. So that's the issue of orientability. Again, we don't want to get too much into the topological and geometric details of it. It's sophisticated indeed. But yeah, so just be aware that this issue with orientability comes from genuine concerns, because some counterexamples do exist. So once we know that a surface is orientable, so if a surface is orientable, then we can make a consistent choice. Here you can replace it with the continuous choice of a unit normal vector at every point. So given given parameterization RUV of a surface and a vector field F, we define the integral over S of this F dot ds, mimicking what we used in line integrals, integral of f ds over the curve versus integral of the vector field dot dr. So that's the analogy. And this will be, okay, this is the domain of parameterization Now, when we have UV, our UV is a point on the surface, and the vector F assigns a vector to that point. So you are on the surface, and there is the vector F at that point. And then we will have this normal vector. We saw before that this RU cross RV is actually perpendicular to this surface there. And now we don't need to take absolute value. We do want a vector, so we dot product. So that vector dot products into F, and you get a scalar function. And now we integrate du dv. So that is the definition of integrating a vector on a surface.